Today I'm going to present my project that I've made for the Emertxe internship. So here I've developed a real-time EV ADAS system, which is an advanced driver assistance system, which is built on STM32F103C86 Blue Pill microcontroller. I've stimulated it using the Pixim lab. Along with it, I've used a VSP tool, Teraton, and finally I've made a Python dashboard. So I'll be diving deep into this presentation and on how I've made the project. Now, moving to the functions and what all the dashboard does. It provides a real-time EV sensing. So basically the system continuously measures the speed, battery charge, torque, power. Then about the ADAS safety. So for the safety reasons, and we have used the three ultrasonic sensors, and here I've used HCSR04 in my project, which helps in warning about the collisions and blind spots. It also helps with the parking. Third is the state machine. This shows the different states the vehicle will be depending on. The main states are parked, ready, driving, regenerative braking, and fault. We'll be diving deep into all these states in the upcoming slides. The next is the telemetry. Now, telemetry is when the data that is packaged, it is sent to the Python dashboard, which is finally how we are planning to visually represent all the data that we have received. So that data is sent through a UART communication. Now, UART is a serial communication protocol which is used for transferring data. Now, using this telemetry, a person can watch it live on the screen or any user. Now we're moving in to the architecture now and each steps that are used to implement the project. Now, first is the base layer, which is the perception. So here this is to give a main idea about how this works. And it is first is the hardware components used is STM32 Blue Pill microcontroller. Now this helps in running the which acts as the embedded processor in the project. It helps in directly interfacing with the physical hardware or sensors to read any raw signals. Now next is the sensing layer. So here for sensing, as I've mentioned, we've used ultrasonic sensors. In the project, I've mainly used for front, left, and right obstacle detections. It measures distance to nearby objects in these three distance that I've mentioned. Then the next is the transport. Now transport is the transmission of data that is referred to. And I've mentioned we've used a UART for the same purpose at a baud rate of 115200 bit per second. Now this serves as the data communication between the embedded microcontroller and the host computer that we are using. So this establishes the connection and we can send data and the values that we'll be processing. Next is the application. Now application is where we are finally displaying all this data into a Python dashboard. Now this gives a very visual representation to the user. In a more easy way, the user can identify according to the speed and brake how the alert it will be getting. That is our final step in the project, where we're creating a user interface that runs on the host PC. Now moving on to the different states, as I mentioned, I'll be diving into. There is parked, ready, driving, regenerative brake, and fault state. So now in this, the parked state, which is the first state that, or the starting state that we're going to. Now in parked state, all the outputs will be off. So here the system is just getting started. And next is the ready state. So ready state is when the system will get triggered when the acceleration pedal is pressed more than 2%. So I'll be showing the Pixim lab in how the brake pedal, how you can vary it. So here basically if you press the accelerator pedal more than 2%, the system will get triggered to the ready state. So here the motor gets armed and the sensors are all turned on. Next is the driving state. In driving state, the system will get triggered when the acceleration is above 5%. And in this now, it's finally active and the data will start streaming. According to when you vary the brake and accelerator, the values will be shown in the virtual terminal and the data transmission starts taking place. Next is regenerative brake. Now this is when you press the brake more than 10%, the system will get triggered and it goes to a regenerative state. Now during this state, the motor will act like a generator. So because it acts like a generator, there is a brake that's getting regenerated, due to which the battery also starts charging bit by bit. Next is the fault state. Now, fault state is when, as the name indicates, it's basically if there is any damages or any warnings. So it's usually triggered when there is any overheating, when there is very low battery or any collisions. During this state, this motor power is cut off and the alarm starts buzzing. Now, when you're in fault state, now and you have to go back to parked state, you can't just force it back. So you have to manually type a command that is fault clear. I'll be showing the code and how you'll be have to type it in the UART shell. Now UART underscore shell is a file that you'll be creating in the STM32 cube ID, where you have to type fault clear so that from the fault state the system can go back to the parked state. Now the next is moving to the thresholds, which shows any warnings and how the type of spare parts we have used. Now the first is the front sensor. In front sensor, the warning will take place when it's below 50 centimeter or if there is any collision. Now TTC basically refers to the time to collision. That means if there is any collision within 3 seconds, here the threshold is 3 seconds. So if it's below that, then there is a warning, and it's very critical if it's below 20 centimeters or when the time to time collision is 1.5 seconds. Same with left or right, and the motor temperature. Motor temperature is usually it's better to be above 70 degrees Celsius. Now all these are thresholds that we have set. It can be varied according to different projects, but I have used this as my thresholds. And for battery, the warning will be below 10%, which means it will force back to the fault state if it goes like below 2%. Now moving to the spare parts, here I've used the first is the PA01, PA1. Those are the potentiometers that I've used for different uses. And as from the name, the first PA0 is used for the accelerator pedal position. Then the second one is PA1 is for brake pedal position. Third is PA2 is for state of charge. Now state of charge is basically the battery percentage, or how much it stimulates the current battery percentage. And the last is the motor temperature that I have named it as M temp, which refers to PA3. This motor temperature is basically for real-time heat generation in the system. Then the next I have used is the LEDs, which is alert indicating for the ADAS system. Now in the LEDs also I've used like 4 LEDs, PA8, 9 and 10. Yeah, then now the what it uses now BSD allows this for the left. For the left one, it is indicating the left blind spot detection. So if there's an alert, it is likely to blink. Same with the right. Then the CLSM is basically collision warning. So if there is any collisions, it blinks for safety alerts. Next is the obstacle detection. Now this is where we use the ultrasonic sensors, as I have said, HCSR04. So in this there we have front, left and right. We have assigned for each side sensors. The front sensor, it will monitor the distance to the vehicle or if there is any obstacle that is ahead of it. Then with the left sensor, left sensor basically feeds the data to the left blind spot detection. As I have mentioned, the LED, the left is basically, so according to that it will blink, or the LEDs won't blink according to the data that is sent from the ultrasonic sensor to the BSDL. Now, fine, last we have used a VTerm. VTerm is basically a virtual terminal that through which data we can see the data that's printed. Now this handles, now the RX and TX, as you can see, is the transmission and receiving of data. We have connected it to two different pins. So this setup basically handles the serial data communication for telemetry of data. Now, if we, because we're using this virtual terminal, we can see the live data that's been printing due to the brake and acceleration pedals, etc. Now moving to the different modules that we have used. Now this is an important part where we have coded in STM32Cube IDE. These are the main modules that I have used, EV control.c. So in this, we are making this file to handle vehicle speed, torque, or power. As I mentioned earlier, it's about the EV controller. So for activating EV controller, we have used EV underscore control.c file. Then we have ADAS.c. This is for handling safety. It calculates the time to time collision, decides the blind spot and parking alerts. Next is ultrasonic sensor. It's for distance calculating. So how it's in the code is basically it converts the timing signal into a distance. So that's how it reads if there is an obstacle behind, front, left, or right. Next is fault. Fault.c is for fault managing. It watches if there is any danger and it will forces the state into the fault. It also manages the timer. Watchdog is the type of timer. Next is UART shell. Now this is where, as I mentioned, we put in the command for forcing it back from fault to the parked state. You have to fill in the command in the UART underscore shell.c. Sorry. Now in this, it will be handling the communication, the serial communication, receiving and sending of telemetry data will be handled by UART shell. Next is the final is main.c. This is where all the data gets looped together, and this will again refresh the watchdog timers and combines basically all the data into one. Now this is the coding part. I have not shown every file. I wish this is basically adas.h file. As you can see on the top, there is fall.c UART shell all, and I have built this project, and it has shown there is no errors and warnings, and I've again built it to make a binary file which is adas underscore dash b. Now in this is the file that you will be using in PiximLab to load the binary file and run it, which is when you will get the output and the values. Now this is the virtual connection. Now I've used VSP and Teraterm for virtual connections in my project. Now VSP is basically virtual serial port emulator. Now why I'm using VSP is because that I'm not making this project in an original hardware. I'm using it in a online software. So there is no physical port for the UART data to travel. So I've used a virtual pair to connect and make COM ports. So using that, I can connect my host, and I can connect uh, the PiximLab data and the Python dashboard so that I can get data. So I used VSP to create a virtual pair, and I have assigned COM6 as my Teraterm, and this is when the data is loaded. This is the message EV ADAS system is ready, and below that you'll be getting the values. So this will be the output that you're supposed to be getting, and this is what I've got when I ran my binary file in the PiximLab. Next is Teraterm. Now Teraterm is again a similar, uh, but Teraterm is where you get the data, where you can see the system is ready. VSP is where you establish the connection between the Windows and this Teraterm. So that is where you assign which COM port you need for the project. Now, next is about the controller module. Now, EV controller module is discussing this because it's a main part of the project. Where so now we're using the EV controller basically to protect the vehicle. So if there is something that you need to manage the speed, torque, or battery drain, we're using the EV controller module, and these are the two files. So in this, you'll be dealing mathematically on how you are calculating the torque or drag and mass factors or even speed. So these are the formulas that are used inside the code itself to calculate the distance or speed, etc. Because we have certain thresholds that we have set. So for blind spot detection or for time to collision, you need a particular threshold. So if it crosses it, then there is a trigger. So you have to calculate it mathematically for better accuracy. Next we have is the fault management. Now fault management is, again, as in the name and we have discussed earlier, it's uh, to manage any damages or any warnings that is given out by the system. So on entering the fault state, the motor power, the PWM basically, which is the motor power, will get cut off and no torque will be produced when it is in that state. So the red LED will turn on because there is a warning and the alarm buzzer sounds. So basically in our dashboard there will be a red fault band. So I'll be showing that in my video how when it goes to fault state, the red color, the dashboard will be showing a red color, so which basically shows a alert to the user. And we have to type, as I said, fault clear in the UART shell to make it from fault to parked state again. Now I'll be showing a video to summarize all this where I've used the Python dashboard. So I'll be playing that video first. So this is when I finally loaded the data. This is the initial stage where it's normal. There is is still going to come into the Python dashboard. This is the Pixin Lab spare parts, and this is the microcontroller blue pill. Now I'll be showing you the fault state mainly, where I'm going to reduce all the brake and accelerator values to very low, and you can see the changes accordingly to the in the Python dashboard. Yeah, so when I made changes to the accelerated pedal, you can see that it is in the critical mode. So as you can see, it is showing a red color. Now this is what I was saying about the fault mode. It shows there is an alert and the user will get notified about the same. Now that's the end of the project. Thank you for listening.